Welcome to this explainer. Today, we're literally cracking open the hardware that powers our entire digital lives to look at the fascinating architecture of the modern graphics processing unit, or GPU. Whether you're exploring a massive, cinematic virtual world, training a complex AI model, or honestly just enjoying the smooth window animations on your computer's desktop, you are relying on a GPU. So let's look under the hood and see exactly how this incredible piece of tech actually works.
Right off the bat, you might be wondering, why does a computer even need a completely separate brain just for graphics? Why do things like rendering a 3D world or training AI require a totally different approach than what our main computer processor, the CPU, can handle? Well, it all comes down to the fundamental difference between doing a few really complex tasks incredibly fast and doing millions of simple tasks all at the exact same time.
Okay, here is our roadmap for today. Number 1, the power of parallelism. 2, inside streaming multiprocessors. 3, VRAM and memory hierarchy. 4, the 3D graphics pipeline. And 5, tensor cores and AI. Let's dive in.
Section 1. The power of parallelism. Think of a CPU like a single, incredibly fast sports car. It's highly optimized for low-latency serial execution. It can get one passenger to a destination blindingly fast. But a GPU? A GPU is entirely different. It's more like a massive fleet of city buses. Now, individually, a bus isn't nearly as fast as a sports car, right? But if you need to transport 10,000 people across town at the exact same time, that fleet of buses absolutely maximizes high-throughput parallel execution. To put that into perspective, a typical CPU might have somewhere between 4 and 24 really complex cores. A modern GPU, on the other hand, packs in thousands of simpler cores designed to process tons of operations simultaneously.
Section 2. Inside streaming multiprocessors.
So, the basic building block of a GPU isn't actually a single core. It's a structure called a streaming multiprocessor, or SM, though AMD prefers to call them compute units, because, tech giants literally never agree on naming conventions. Anyway, think of an SM as a self-contained processing factory. A modern GPU is made up of dozens, sometimes even hundreds, of these factories all operating independently. Inside each SM, the hardware uses what's called a single instruction, multiple data, or SIMD approach. This basically means the SM can take one single instruction, like say multiply by 2, and execute it across dozens of different pieces of data simultaneously. If we look even closer at the components of an SM, we see they're packed with highly specialized tools. They contain CUDA cores, which act as the arithmetic logic units for basic math. They feature special function units for really complex calculations, like trigonometry. But crucially, they feature massive register files and shared memory. Because GPUs rely heavily on hardware multithreading, they can hold hundreds of execution contexts active at once. If one thread stalls out while waiting for data to load, the SM instantly switches to another thread, completely hiding the latency. Basically, no core is ever left sitting idle.
Section 3. VRAM and memory hierarchy.
Inside a computer, we use different types of memory to balance speed and space. SRAM is used for cache right on the GPU chip. It uses 6 transistors per bit, making it blindingly fast and incredibly stable. But it takes up a lot of physical space and is quite expensive. Think of SRAM as the top of your physical desk. You can grab things instantly, but your space is pretty limited. Conversely, DRAM, which is used for the GPU's main VRAM, uses just 1 transistor and 1 capacitor per bit. It's incredibly dense and cheap, acting kind of like a massive filing cabinet. However, the capacitor constantly leaks electrical charge, so it actually has to be dynamically refreshed over and over, which is exactly why it's called dynamic RAM.
Because the GPU values massive throughput over absolutely everything else, accessing that DRAM filing cabinet has to be highly optimized. Instead of fetching data one tiny little piece at a time, VRAM relies on incredibly wide memory buses, sometimes 256-bit or even 384-bit wide. The memory controller groups or coalesces requests together to synthesize huge chunks of data simultaneously. This is exactly how modern GPUs can deliver hundreds of gigabytes of bandwidth per second to feed those thousands of hungry parallel cores.
Section 4. The 3D graphics pipeline.
Historically, the graphics pipeline functioned as fixed hardware. If you were playing a 3D game back in the early 90s, the hardware was a literal assembly line, where data passed through incredibly rigid, unchangeable stages. But today, thanks to the unified shader architectures that emerged in the early 2000s, this pipeline is largely programmable.
It acts like a sequential factory floor passing streams of data through both fixed-function hardware, like texture filtering units, and highly programmable software shaders running on those streaming multiprocessors we just talked about. The modern pipeline follows 5 major rapid-fire steps. First, vertex processing transforms the 3D coordinates of an object into a unified spatial system. Second, primitive generation groups these vertices into shapes, which are almost always triangles. Third, rasterization densely samples those triangles to figure out exactly which 2D screen pixels they overlap, turning them into what we call fragments. Fourth, fragment processing calculates the precise color of each fragment based on simulated lighting and draped textures. And finally, pixel operations check the depth buffer. If the fragment is actually visible to the camera, it gets pushed to the screen.
So what you end up with is the final output of millions of independent parallel calculations perfectly converging. The GPU is tracking millions of vertices, rasterizing them into millions of fragments, calculating the balance of light, and checking depth visibility. And it is doing all of this up to 60 or even 120 times every single second just to create a seamlessly lit and textured 3D form. It's honestly mind-blowing when you think about it.
Section 5. Tensor Cores and AI. As deep learning started to really take off, engineers realized that training a neural network is essentially just doing massive amounts of matrix math. And guess what? That is a task perfectly suited for the GPU's parallel nature. But they wanted to go even faster. Enter tensor cores. Unlike standard CUDA cores that process scalar operations one by one, tensor cores are highly specialized hardware units purpose-built to chew through entire 4x4 mathematical matrices, multiplying and accumulating them in just a single clock cycle. To maximize this efficiency, tensor cores allow AI frameworks to dynamically alter the precision of their math. Standard graphics often require 32-bit precision to look right. But AI? AI is remarkably resilient. By dropping down to 16-bit or even 8-bit precision formats like FP8 or INT8, tensor cores can process data at absolutely astonishing speeds. Lower precision means less memory bandwidth is used, which results in vastly higher throughput. This architectural leap is a real game changer. It can literally turn what used to take hours of AI model training into mere minutes.
So what started decades ago as a rigid, fixed hardware pipeline designed strictly for drawing triangles for video games has entirely transformed. Today, the GPU is a massively programmable, heavily parallel supercomputer sitting right there on your desk or scaling up within massive global data centers.
And that leaves us with a fascinating final thought. We are currently seeing a massive convergence in hardware. CPUs are adding more parallel features like higher core counts and wider vector instructions, while GPUs are becoming infinitely more flexibly programmable to handle general compute tasks. As we push the boundaries of AI, real-time ray tracing, and edge computing, where is the ultimate ceiling for this incredible parallel architecture? Will the line between CPU and GPU eventually vanish entirely? Thanks for joining me on this explainer, and keep questioning how the digital world around you is built.